Hi all, this is Mr. Yeager for On Level Chemistry. Welcome to the chemistry course. This would be the first video to start with as we start our first unit on atomic structure and nuclear. And our first lesson is on I would call it history, but we're going to see right here the development of the atomic model. Okay, you might know from prior courses, that hey, we know atoms are made up of protons, neutrons, and electrons on the inside, but we didn't always know that. We didn't even know substances were made up of atoms originally in any way, and it took a long time, a very long time, for there to even be proof that there even had the atom, and then we had to even go farther to the subatomic particles. Okay. So that's what we're going to look at. We're going to look at the different models, the most popular models that kind of came up. It's a great showing of science developing about the atom as we understand the pros and why we thought the atom would appear something like this, but then immediately understand that there's clear limitations to what this model might not really fit how we actually look at everything with it. And even with our most modern model, because we can never actually physically see the atom, it's something that we're going to continue investigating, even though we have very, very good evidence and proof now of, I'll say evidence, I don't want to call it proof necessarily, but evidence of what the atom should look like. Okay? So I'm going to start off with this. The original kind of idea of what all substances were made up of. Again, that's what chemistry is, the study of substances and their reactions to each other. The initial thought was simply that all substances were made up of the 4 natural elements in the world, which would be fire, water, wind, and earth. All right, and that was kind of the original, like you mix these things together and you create different substances. All right. So if you play some like fantasy video games, that's why those are always like the most common like elements used in magic spells and things like that, because you thought that you could create things out of that. So here we go. So the first kind of strong model that came up for the atom, we're going to call it the billiard ball model. This is not what it was actually called, okay? Because this is the first model that was created by a philosopher named Democritus. Democritus did not play billiards. He did not play pool. Okay, they did not play that back in ancient Greece. I don't believe they did. I don't know when billiards started. All right, but we're going to use this as kind of an idea. I want you to think of an 8-ball or a cue ball. Okay, because what Democritus proposed is that all substances are made up of very, 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 very tiny particles, which he called atomos. But obviously we changed that to atoms. We got rid of the 1 O. And he said all substances are made up of these atoms, and these atoms are these hard spherical objects that come together, that create wood, that create rocks, that create glass, that create whatever. Okay? And they're these hard spherical objects that are created. He didn't do a single experiment. It was all just a thought experiment, you could say, because again, it was a philosophy with it. Okay, so but it gave us a starting point, and I mean, again, you'll see he was right that they're spherical. Okay, but there are clear limitations with this. Okay, it doesn't have any subatomic particles. He thought this was the smallest particle out there, was the atom, and atoms are broken down even into smaller, and we've learned even smaller particles. Okay, so no subatomic particles in this, what we call billiard ball model. Okay, it also doesn't account for what we're going to learn about later called isotopes, where we have atoms of the same type, but they have different numbers of neutrons or different masses. Okay, so he thought, if he has iron, they know in ancient Greek they knew what iron was, they knew what gold was, they knew what silver was. He believed that every single particle, every single atom of silver was identical, and we now know that's not true. Okay. All right. We then jump many years. Okay. I think we get almost all the way up to like the 1800s, if I believe I'm correct with this one. And we get to what we're going to call the chocolate chip cookie model. This is actually for those people that know a little bit more about the models. It was originally called the plum pudding model. because it was created by a British scientist, and plum pudding is a very common dessert treat. But I mean, we don't know what plum pudding is. I've never had plum pudding. So we're going to look at this as chocolate chip cookie dough model, okay, or chocolate chip cookie model. So what this is we started understanding, we had more instrumentation now. Again, we're jumping from ancient Greek up to the 1800s. So clearly plenty of advances during those 2,000, 3,000 years, all right? And we now know about charge. We've learned, the scientists understand, chemists understand, physicists understand that objects do carry charge. And based on some experimentation, there was an understanding that the atom has a positive charge to it, but that there are these little particles called electrons. I mean, this is where we first discovered electrons, okay, or proposed electrons. There are these particles that clearly are moving around this positive blob, okay, so the positive dough, all right, and then these little chocolate chips, these negative electrons, are moving around because when we shot negative beams through it, basically we call them cathode rays, we saw that they would deflect a little bit. They wouldn't just go straight and travel straight through it. There'd actually be some attraction with it as it went through. Okay, so at least we are actually getting to our first subatomic particle being introduced, the electron, within this kind of positive, I'm going to call it soup, but again we'll use dough, whatever you want to say with it. Okay, so limitations. There's no nucleus to this atom. Okay. There's no center to it. It's just this kind of, again, spherical mess, but with nothing more than these little tiny chocolate chips of electrons throughout it, okay? And it doesn't explain how positive charge holds electrons inside the atom. Okay, yes, we know that this area has positive charge, but why? Okay, and why is that keeping these electrons sort of bound within the atom some? So finally we get to something that obviously is getting much closer to it, and this was a very, very popular model for a period of time. We are getting into the 1900s now, so we're getting almost there. I know we're still 100 years away from us, all right? But another scientist came along, did a very impressive experiment, shooting alpha particles at, I forget, I think it was a gold plate, and he realized that some of these alpha particles would be completely deflected back toward him. He was expecting for them just to go straight through, but certain ones actually shot straight back at him. Again, and I say shot, he had detectors that would detect that some of the alpha particles would hit this and come backwards instead of all going through, okay? And so he realized that there must be a very small, because again, it didn't happen often, but it did happen, a very small center that was large enough to deflect an alpha particle, which is the size of a helium nucleus, all the way back at it. So it must have some mass to it, and since it repels it, must be positive charge. We'll learn later in the unit, alpha particles are positively charged. All right, so this at least gets us to the idea, and so he proposed there must be some sort of positive nucleus with the electrons orbiting around it, or kind of going around the positive nucleus. And so that kind of brings in now where we know, okay, this must be the actual things that are holding the electrons in, and we have this attraction between positive and negative, but we still have some limitations, okay? It doesn't explain why, why don't the electrons just go straight toward the nucleus? If this is so positive in the middle, why do the electrons not just get attracted straight to it? All right, would be the big one. And it doesn't completely explain, we're going to get into this idea of, we're kind of just assuming the electrons are just anywhere, okay? And that still does not explain some other things we see that electrons can do, all right? But we're getting closer. Okay, so we have protons now, we have electrons now. Okay? This then leads to the idea that there must, again, Model 4, this planetary model, we start figuring out that electrons must be on kind of these different little pathways, we're going to call them, okay? We're going to call them later energy levels. And we kind of just assume that they must be kind of going around and around along particular energy levels. And this is based on, again, realizing that electrons start emitting some light and other things like that based on how you heat them. So we're at least starting to organize the electrons a little bit, okay? One of the issues, though, is this worked really well for hydrogen, but didn't completely explain any other atom very well, okay? So, you know, we like that there must be kind of this orbiting idea. That's a very common way of explaining the atom to beginners, but that is, again, not the real way that it works, okay? The Jimmy Neutron model, okay. Again, this is not the name of the actual model at all. What this is basically introducing is in the 1930s, we realized if there's a positive center, this goes back to what we said with the model, the nuclear model, okay? We don't have stability. If we have all this positive charge in the middle, how could it possibly be sticking together? How could it be staying together? So we have a scientist that came along, his name was James Chadwick. He was able to do experiments and actually determine that there must be some neutral other particle in the nucleus, and he called that a neutron. So that's where we get the neutron model. So we're introducing that basically there is neutrons in the nucleus now. There's protons and neutrons. So that leads to more nuclear stability. But again, it doesn't eliminate the issues with the electrons. Okay, it still doesn't explain the behavior of the electron. So it's just the idea that we kind of, you can see how we keep on piecemealing this. And going back to like the prior model, at this time, people were looking for something else in the nucleus that would hold together. It's just nobody could prove it until James Chadwick came along and actually was able to illustrate that neutrons are there. Okay. And then probably what would be our most modern model now. We get into quantum mechanical model. Yep, okay, quantum mania. This is obviously the most modern model, but one we're continuing to play with quite a bit, okay? It does support the idea that electrons must be in particular energy levels, and it gives us a much more clear idea of where they are, all right? But again, all within a probability, okay? We're not going to get too technical with this. There's a lot to this particular model. Quantum is a very, very interesting subject that continues to be studied and played with, and a lot of it has been shown to work very well in explaining what goes on around us. That's what we do with any theories, is it's trying to help explain what's going on around us. The things that we continue, as it says, it's complicated. Okay, it's very difficult to understand. That's really our big limitation. And as I said, you can never exactly know where an electron specifically is. That gets into something called the Heisenberg uncertainty principle, where we can never know an object's exact location and motion at the exact same time. If the basic idea of that is, obviously, if it's moving, it's constantly changing position, so how do you know where it is? So that's where we lead to probabilities of where objects are and where these electrons are. But that is the final part of the model. With the quantum model, I'll just kind of say, we continue to look more deeply into why it works, and that's where chemists and physicists, you'll see there's a lot of physics in chemistry, that continue to try to figure out what is like the original particle that is going to create all of this, that started all of this. So anyway, that is our final model. There you go. So we went through the different types of models. We went through kind of the progression of why we thought they were good, what's the issues, the limitations though, and that's what you got to remember. Thank you.